Good morning, ladies and gentlemen. Here we are, section 13.4. This is going to be talking about radical function transformations. Basically what that is pay close attention, it's a shortcut to graphing, so we don't have to make a whole bunch of ordered pairs. So we're going to finish that up today. Tomorrow we're going to do day 1 of 13.5, day 2 of 13.5, and then Friday again we will have another formative on its learning for you to complete. We'll probably open that on Thursday afternoon. Let's see if we can't get everybody to take it this time. Then from here, this is not your notes. Why don't you hit pause, grab a piece of paper. Are the following functions inverses of each other verified algebraically? What that means is you need to find out what does f of g of x equal, and what does g of f of x equal? And remember, it can only equal one thing to say whether or not it is a function or not. So why don't you hit pause and give this a shot? I will be back with the answer. Okay, so what we want to do is we want to plug g over here. Where are you, g? We want to plug g into f, and then when we plug g into f, that just replaces that x in there, and now I got to let my mathematics do the work. So the 3's reduce, and that gives me the cubed root of x cubed plus 10 minus 10. Well, that's a big grouping symbol underneath a root. I get the cubed root of x cubed is the cubed root, or is just x. Then I got to not only find f of g of x, we got to find g of f of x. And what I got to do is plug that in. So as I'm coming through here, this cube gets rid of that cubed root, and I have 3x minus 10 plus 10. I can see these 10's go away, and what happens is I have the 3's will reduce out, and g of f of x equals x, because both of them simplify exactly and only to x. Therefore, yes, they are inverse functions of each other. Okay, that's what we did. That's what we did yesterday. So what we're going to do here, there's a whole lot of shifting going on. Bottom line, what we're going to do is we're going to look at two new parent functions. And parent functions, these are the points, okay? The cubed root parent function and the square root parent function. These are the points we want our brain to see when we are going to graph any of these cubed roots or square roots. And because this is a square root, I can only put positive numbers in for x. And if I put in a 0, I get out a 0. Okay? And there's my starting point, is what I'm going to think. Well, the next perfect square is going to put a 1 in. That gives me a 1 out. And then after that, I want to put a 4 in. That's going to give me a 2 out. So that's 2, 4. I'm going to be up 2. I could continue on. I could put a 9 in. The square root of 9 is 3. And that's going to put it up here. But bottom line, a square root function is a hook, and they're all going to look like that. The cubed root function, well, the cubed root function, I'm going to start with 0, 0 here, and I'm always starting here, so that's going to be my starting point right there. Here's my starting point for the square root, here's my starting point for the cubed root. Well, if I put a positive 1 in, the cubed root of 1 is 1, so then I get a 1, 1. The next perfect cube, well, that's going to be 8, because the cubed root of 8 is 2, because 2 to the third power is 8. So I'm going to go over 8 up 2. And the other thing I'm going to do is, because this is an odd root, remember, just because it's an odd root, I can put negative numbers into odd roots. So it's going to give me a negative 1, a negative 1. How about a negative 8? That's going to output me a negative 2. And my cube root function is going to kind of look like a sideways S. Notice, just like we did, the domain of that thing is all real numbers. The range is all real numbers, but the domain and range of an even root function is restricted. Okay, so every time we graph this cubed root, we want these 5 parent points I'm going to talk about. And over here, we're going to talk about really these 3 parent points, because 9's just getting a little nutty, and I don't need that out there as much. Okay. So now what we're going to do is we're going to say, hey, what happens if I add a 3 underneath that square root? Well, what is that doing? Well, remember, our original function started here, that pulled it this way. How many units? 3. And our starting point on a cube root is always going to be that S. What did that minus 4 do? Well, that pushed it to the right 4 units. And then look, from that point, I go over 1, up 1, and I go left 1, down 1. And if I went 4, 5, 6, 7, 8, down 2, those parent points I was talking about are right there. So I can find a new little place to start these. And whereas this one, oh, that's 2. What happened from my starting point? I went over 2. Okay, so adding and subtracting under the radicals appears to move the graph in which direction? Okay, explain how you know which way it goes. Well, it is a horizontal transformation inside opposite. Okay, so that was a +3 in there. So rather than going 3 towards the positives, we went 3 to the negatives. Rather than going 4 to the negatives, we went 4 to the positives. Rather than going 2 to the negatives, we went 2 to the positives with our starting point, okay? Well, what happens in the next one? Well, let's try one. Let's try to write this equation. Well, here's my starting point, right? That starting point is from where I typically start. It is over -2. Well, that means f of x is going to equal, because it horizontally shifted it, it's all going to be my x, and I'm going to say opposite the sign, I need opposite of 2, so I would add 2 to get that. Over here in this one, here is where I'm starting from, here's where I typically start my parent function from. So that's going to be f of x equals, I know it's a square root because it's that hook going out in that direction, and that's a +3, so it's going to be x, the opposite of +3 would be -3, and that would be the equation of that one. Well, here I'm looking at my cubed roots. I know this is a cubed root because it's sideways, and here's my starting point. It's right in the middle of that little s. Well, notice that's that way 4. So my function is going to be the cubed root, because it went horizontally. I have my x, and if I add 4 to that, that's going to make it go -4 the opposite way, because it's inside opposite. This is going to be a +3. So this, again, I know it's a cubed root because I can see it's going in both directions. X, and it's a -3 because it went to the right 3 units, so it's the opposite of that, which would be -3. That's all we need to do that with, okay? And you can hit pause and rewind this anywhere you want. Well, what does the next one do? Oh, check it out. Now we are adding and subtracting on the outside of the root. What did that do? Well, in this first one, it took my starting point and it went up 3. It took my starting point here and it went up 4. What did it do here? It took my starting point and it went down 5. Adding and subtracting outside the radical appears to move the graph which way? Vertical. Except this time it goes vertically the same as the sign. Okay? So, because that's a +3, my starting point went up +3. And then from there, I went over 1, up 1. I went over 1, 2, 3, 4, up 2. And I went over 4, 5, 6, 7, 8, 9, up 3. And you see those parent points I had there? I can do that after I shift it up to 3. I can make my graph right there with those parent points I have. Well, let's write a few equations here. Well, this is starting here at +2. It's a hook. So I know f of x is going to equal the square root of x. And because it didn't go horizontal, I'm not putting anything underneath the root. But because it did go up 2, I'm going to put the same sign on that 2 for my vertical. This one here, here's my starting point, okay? So f of x equals, it didn't move horizontally at all. So I'm going to not add or subtract anything underneath that root. But it did go down 2, so that's why I'm subtracting 2. And the same on these. Here's my starting point. Here's my starting point. These are cubed roots because they're going in both directions. So I know f of x equals the cubed root of x. And I'm not putting anything underneath that ginormous thing because I see it went down 3 units. And that 3 cannot be underneath that root. This last one went up. So that cubed root of x, it went up 1, 2, 3, 4. So I'm going to add 4 to the outside of that to show it's pushing my graph up. Okay? So what are we going to do here? Let's put them all together. Well, here is my new starting spot, -1, -3. Because that's a hook, I know f of x equals, it's a square root, And because it moved to the left 1 unit, I know I'm going to have an x plus 1 because it's opposite the x, same as the y. And over here, I'm going to go, this is the ordered pair 2, comma 4. Well, f of x is going to equal inside opposite. Inside is the x, so I'm going to put a minus 2 because I wanted to go right 2, and I went up 4. And then from there, check it out, I'm going over 1, up 1. I'm going over 1, 2, 3, 4, up 1, 2, and so forth to make those graphs. Okay? Well, here, a lot of people get all wigged out on the cube roots, but just remember, they start right in that little s, which is 1, 2, 3, 4, negative 4, negative 1. So f of x equals my cubed root, x plus 4 minus 1. Opposite, same. Opposite of the horizontal, same as the vertical. So then over here, I'm taking this guy. This is 1, 2, 3, comma 2. So this is going to give me my function is the cubed root of x minus 3, because it had to go to the right, so it's the opposite, plus 2 up is what we're doing, okay? So we're inside opposite, outside the same, all right? Now we have a few more going on here, and these are the ones that get a little tricky for you, okay? So if I multiply the inside of my function times a constant in there, like the first one there is 2, and then 3, and then 5, what is that actually doing? Well, we have a couple points on here, and what we're trying to picture is we're trying to picture our outputs, okay? When do I get the square root of 1 underneath there? Well, I would get that by putting a 1/2 in there, right? So in order to get my output of 1, I would be a half. And in order to get my output of 4, I would be putting in a 2. So what that is actually doing, I'm looking for these numbers, right? What that is actually doing is I'm putting in a smaller number to get to the output value I want. So every x I put in here is going to be changed by that multiplier before I take the square root. And what that's doing is that's making that square root actually shrinking, because to get to that square root of 1, I'm putting a number smaller than 1 in to get that 1 out. Same thing over here. To get that over 1, up 1, I would have to put a third in there. I'm putting a smaller number in there to get that square root of 1 out. So rather than putting the square root of 1 in, it's shrinking it down, or it's compressing it horizontally, because this is changing my x value in there, okay? So what that's doing is it's taking all of my parent points, which would have been 1, 1, 4, 2, 3, 1, and it's compressing them over 2, I'm not going to say 2 units, but a factor of a half, okay? It's kind of confusing when you look at this, but what does it do? Multiplying by a value greater than 1 inside the radical compresses or shrinks the graph horizontally. And like I said, okay, that number here, that is inside the radical, that number 2, is changing what I am putting in. So because it's changing my input value before I take the square root, it is doing something horizontally. And because I'm putting a smaller number in to get that first perfect square of 1 that I want, it is compressing my graph, okay? And let's look at number 3. Well, what happens if I put a number less than 1? Well, if a number greater than 1 compressed it, okay, a number smaller than 1 is probably going to stretch it, but notice that half there is going to affect what I put in. Well, now if I put a 2 in for x, to get to that square root of 1, it's stretching it out to 2. Okay, so now it's really going 0, 0, and I could say if I went over 2, I'm really going through this to go out. And I can see it's still increasing. So that 1/3 to get, I got to go over 3 to get up to that 1 now, where typically I go over 1 to get at that 1. Okay, so it's horizontally stretching my graph. The inside ones are kind of kind of tricky, but when we multiply a value between 0 and 1 inside the radical, it stretches the graph horizontally, okay? And in order to figure out, and in order to keep these straight, okay, we are trying to find, okay, when we're trying to make these graphs, we are finding input values that result in finding, when I take the square root, I want a perfect square underneath that because we don't want to rely on a calculator to do everything we are doing here. So we are thinking about it before we go in. We want perfect squares to do that. And with the numbers, I am plugging in when I'm multiplying underneath the root by a constant. To get that perfect square, that number is changing what I'm plugging in. That's why it's horizontally affecting the graph, okay? And we're there, and now we're going to hit. Well, what happens if I multiply on the outside? Well, you see I can put these same exact parent points in. So like when I put a 1 in, I can take the square root right away, or I put a 4 in, I can take the square root right away. Well, now that that number is on the outside of the function, that number is only affecting my output values. So what it's doing is when I typically go over 1 up 1, it's going over 1 up 1 times 2 to 2. Typically I go over 2, 4, and I usually go up 2, but now it's affecting my output, so now I'm going up 4. So with that number greater than 1 on the outside, as you can see with the 3x and the 4x, what that is doing is that's vertically stretching my 1, 1 up to 1, 2, my 1, 1 up to 1, 3, my 1, 1 up to my 1, 4, whatever that stretch value is, okay? So when that number on the outside of a radical is greater than 1, it stretches the graph vertically because it is changing the output value, not the input value like it was before, okay? It's not making it, that number is not making me pick and choose different numbers for x to get to the perfect square. I'm just putting my perfect squares in, so it's changing it vertically. Obviously, if that number is smaller than 1 on the outside, it is going to compress or shrink your graph, okay? Normally, I would go over 1 up 1, but now I had to take that 1 times my half to get a half, and then I'm at the half. Typically, I go over 2, 4 up 2, but now I got to take that 2 times my half, and it gets me 1. It's just bad calibration when I graph those little buggers. Okay, so it's shrinking those parent points down. It is compressing them down and squishing them vertically, okay? So when you multiply by a value between 0 and 1, it, outside of the function, it compresses vertically, okay? So what I'm going to do here is I'm going to write something on here. And we have, say, f of x equals, and I'm just going to call this an a times the square root b x minus c plus d. I'm going to throw a whole bunch of things in here at you, okay? And this is what these are all doing. What is this doing? Horizontal, opposite sign. Okay, it's a horizontal shift opposite the sign. Well, what is this plus d? That is a vertical shift. Same as sign. Okay, now when I'm multiplying the outside here by something, that is a vertical stretch slash compress. And notice it's a stretch if a is greater than 1. And it's a compress if a is greater than 0 but less than 1. Okay? And then what is this b guy doing in here? This is horizontal stretch slash compress. And it does everything just the opposite. Okay? So if b is greater than 1, it is going to compress it because I have to put a smaller number in for x to get those perfect square numbers. If b is greater than 0 but less than 1, it is going to stretch the graph, because then figure out b has a fraction in there, and I'm putting a bigger number in there for x, stretching it out sideways to get where I need to be, okay? And that's kind of what they are. And we are just going to come through here, well, negative, well, if I put things in, I got 0, 0, I got 1, negative 1, and I would have 4, negative 2. So that is affecting my outputs again, but I'd go over 1, down 1, I'd go over 2, down 2, and what did that do? How about this one over here? Well, now I have my parent points of 0, 0, 1, 1, and 4, 2. But notice this negative on the outside, and it's a stretch. Well, negative 2 times 0 gets me to 0, but when I go over 1, 1 times negative 2 gets me to negative 2. When I usually go over 2, 4, I got to take that negative 2 times this 2, and that's going to take me to negative 4. So I can see the 2 is stretching the graph vertically. See how it stretched my points down? But that negative is reflecting the x-axis. Okay, that's exactly what that negative is doing. By multiplying by a negative value on the outside of the radical reflects the graph across the x-axis is what it does. Okay, and you're going to have some to graph. And I'm going to chuck an example up here really quick, and I'm going to show you what I'm talking about, and then I'm going to finish up the lesson. Okay, so typically when I graph, here's my typical starting point. And then when I look into this graph, I'm going to say, opposite of that is going to be positive 3, same as that is positive 2. So I'm going to move over 1, 2, 3, 1, 2. This is going to be my new starting point that I'm thinking about right here. Now that that's my starting point, now I am just picturing this graph right here, and this is what I'm trying to get at. So whenever I graph that, I think in my mind, put in a 0, get out a 0, put in a 1, get out a 1, put in a 4, get out a 2, right? Those are my parent points. But then this value on the outside, I got to take times the 2, the same way we did when we 149 with our parabola, except now here is the 0, 0 I'm thinking about, because I'm moving my starting point. Then I'm going to go over 1 and up 2, because I stretched it. Then I'm going to go over from this spot 1, 2, 3, 4, and then from here, so I'm thinking 1, 2, 3, 4, and then I'm going to go up 1, 2, 3, 4, and I'm going to get that point, and that's all it takes me to graph my starting point, ignore those, and then just focus on this. Take these parent points that I usually go right here and here, multiply the y value, because that 2 is on the outside, times it, and I can make a graph really fast, and then I can come back and I can say, oh, I didn't even need all of this stuff, and I look really, really smart, because I did it with no work. Isn't that nifty? The hardest part of your assignment here is to come up with an equation. Well, what I want you to think about is these are all hooks. All 4 of these are going to be, all 4 of these are going to be hooks. So I want you to think of, f of x equals the square root of something times x, okay? Because I can see these aren't going through. When I put an x in to my parent function, okay, I know this is not the graph, because when I put 6 in, it doesn't give me that out. So I know somehow that number is being manipulated. So what I'm going to do is I'm going to take that point right here of 6, 6 that I started with, 6, 6, and I'm going to think of, f of x equals the square root of some number times my x. And I know my output is 6, when what do I multiply times 6 to get that a? Well, if a is 6, I get 36 underneath there, right? So f of x must equal 6 times x, because then when I put a 6 in there, 6 times 6 is 36. Square root of 36 outputs my 6, okay? It'll make a little bit more sense over here, hopefully, when we're taking this point here. We have this point right up here is 12 comma 6. Well, think about this. My output is 6. What number, what value, what multiplier am I taking times 12 to get 6? Well, I can think of solving an equation here really quick too, which we're going to be doing. If I square both sides, I'm going to get 36 equals 12a. So a has to equal 3, because 12 divided by 3 would give me a. So if f of x equal the square root of 3 times x, when I put 12 in there, 3 times 12 is 36. You take the square root of that, you get 36. So I'm just solving to find out what value am I multiplying my x by to get there. Here's these last two. These look like they're a little bit scrunchy, but I'm going to do the same thing, and I'm going to say my output is 3. What number do I multiply times 12 to get 3 out? So I got to think more. That's why I like to think about solving equations. So if I square both sides, I'm going to get 9 equals 12a. Well, that means a has to equal 9 over 12, which actually would be 3 over 4 now, wouldn't it? So that means f of x has to equal the square root of 3/4 times x. So if I put a 12 in for x, 3/4 times 12 over 1, well, that's going to reduce that to a 3. That gives me my 9 underneath there to get my output of 3. All right? And the very last one we're going to do over here is this bottom one. And, you know, we need an output of -6. And what multiplier am I going to take times x? But the other thing I need to look at here is this one goes down, this one's reflected across the x-axis, so I do know I need a negative out in front of that. So I know f of x is going to equal negative something underneath there, and then all I'm going to do is, I'm not putting an x in there, that's supposed to be a 9, isn't it? Yes, it is, because we're putting our x in, because we're saying what number times 9. Okay, well, I can divide these negatives off. Square root of a times 9. Then if I squared both sides, that kills the root over there. That gives me 9a equals 36. So what's 36 divided by 9? That would be 4. Okay, so that would give me a 4x underneath there. Now, I want you to know that is not exactly the answer we would like to see there, because 4 is a perfect square, okay? So we're really seeing this as negative square root of 4 times the square root of x, and we know the square root of 4, hey, that's going to be 2 square root of x. This is the function we are really looking for there, okay? And these compressions, these a values, you can find them whether they're under the root or outside of the root. It's all going to work itself out on how they do that, but just write yourself an equation and knock those little buggers out. And from here, you just have your 13-4 homework. Have a great day, and we will talk to you tomorrow.